train scenario, and I got train A and train B, and I'm so tempted to make this like a Thomas the Tank Engine sort of story, but I'm not going to do it. Like, whatever. I got a 10 kilogram train, and it's rolling along at 10 meters per second, so nice round numbers to the right. We should give ourselves a reference frame, because momentum is a vector. So we'll say that to the right is positive and to the left is negative, but this A train is going to bump into the B train, and it's moving along at 10 meters per second, so maybe we should add in some values. VA is 10 meters per second, and I just defined a reference frame, so I'll say that it's positive, and mass A is 10.0 kilograms. And it hits a stationary little 5 kilogram train. So I'm going to say, all right, well that means that MB is equal to 5 kilograms. And the fact that it's stationary, oh, my need for order in the universe is going to, you don't have to erase this. I got to write this way just because I need to have the velocity on top. 0 meters per second. Mass B, 5 kilograms. Sorry, I'm just trying to do it the same order as on the left-hand side. You can judge me, I don't care. All right. Anyway, after the train collision, the little train had a velocity of 8 meters per second. So I'm going to write a little piece of information about that. That means that this train afterwards got knocked forward. Boom. So that it's going to have a VB primed, an after velocity, of 8.00 meters per second. But you know, if you ever take two cars and you collide them with each other, you know that the first one isn't always going to come to a dead stop, right? It's going to do something. Sometimes it rebounds. Sometimes it carries forward a lesser velocity. I don't really know. It all kind of depends on the physical setup of things. And so we notice that this guy gets bumped forward. But what does this guy do? And we should be able to use conservation of momentum to analyze this, okay? So what we would say is, we don't know what VA primed equals, so I'm going to leave this as a blank if I was giving myself my own little personal organizer. But what I do know is that momentum is always conserved. And so I could say something like P total is equal to P total primed. And by the way, momentum being conserved, this is an interesting thing, always happens. Momentum is always conserved. Even if, and we'll talk about it later with elastic versus inelastic collisions, but even when a system isn't 100% efficient in its collision and it loses energy, weirdly, momentum is conserved. I think it's weird because kinetic energy has mass and velocity involved, and so does momentum, but it's still conserved when it's momentum. That's a weird thing, okay? So we're going to circle back to that, but I want to plant the seed right now. So if I expand this thing out, I'd say, okay, well, P total is equal to, well, really it's going to be mass A VA plus mass B VB equals mass A VA primed plus mass B VB primed. Well, primed indicates that it's an after scenario. And I'm trying to get VB primed all by, no, I'm trying to get VA primed all by itself. So what I think I'd like to do, I'm just going to do a math step here where I take one value over. Look, I'm trying to get VB primed all by itself, so I think I can take this term over to the other side. So I'm going to say, all right, MA VA plus MB VB minus MA, don't tell anybody that I didn't align my equal sign, VA primed is equal to MB VB primed. And because I'm a little on the lazy side, I think I'd like to not write a whole extra line. I'm going to whip out an extra color. Yep.
Aren't you trying to get VA, not VB?
Oh, shucks, I am too. I'm so glad you spoke up. I would have isolated VB and then I would have been like so upset in like 2 minutes time. You're right. I wanted to get, just took that MB VB primed over, and I wanted to get MA VA primed by itself. You're right. Thank you. So I'm going to throw in an extra calculation in here, just because I don't want to have to rewrite another line of this. I'm going to divide both sides by MA to cancel out that MA. And that gets my VA primed by itself in a real hurry. So I can say VA primed is equal to MA VA plus MB VB minus MB VB primed all over MA. And I can start subbing in values. And I'm going to fight the urge to try and cancel a mass, because you notice that MA and MB aren't the same value, so I can't just cancel them out. I mean, you could, I guess, try and like factor an MB off of the second two terms, but I think it's just like not very fruitful, right? So I'm not going to do it. Anyway, so we sub in our values, 10 kilograms, VA, 10 meters per second, plus MB, 5 kilograms, times VB, oh shoot, that was 0 meters per second. I guess I could have earlier gotten rid of that as a 0. Minus MB, 5 kilograms, times VB prime, 8 meters per second, all over MA, 10 kilograms. And that's going to spit out a nice round number, actually. I think I cooked this nicely. What do you guys get? Yeah?
6.00.
Beautiful. 6.00 meters per second. And it's even a positive value, right? So to the right. So if I'm thinking about what's happening here, according to these calculations, big old car A bumps into car B gets bumped forward at 8 meters per second, and car A carries on at a diminished speed of 6 meters per second, slower than its original 10. Like, okay, yeah, that seems kind of reasonable if I'm picturing that in my mind's eye, okay? Now, I wanted to come back to this idea about how, we analyze this with conservation of momentum, but is energy conserved? And the check to see if energy is conserved is really easy. We can really treat it like a left side, right side thing. And it's not really left side, right side, it's really before and after. But I say left side, right side because that reminds me of math proofs. We're trying to investigate whether energy has been conserved or not. And so my left side, my before, I'm saying that's EKA plus EKB. And my after would be EKA prime plus EKB prime. So if I was investigating to check to see if energy was conserved in this situation, I could state the question: is energy conserved? I didn't type that into the original note, but that's a good question to ask. So I'd expand out EKA and EKB to be 1/2 MA VA squared plus 1/2 MB VB squared. And then likewise for the after, 1/2 MA VA prime. This is a little bit ugly. I like to put my VA primes in a bracket so it doesn't look like VA to the power of 12. Not that you were going to do that, but It's just one of the annoying parts about prime notation. All right, so I'm ready to sub in all my values. Let's do that. Of course, since car B was starting from rest, that term zeroes out. We just figured out 6 meters per second. And I want to hear from you folks. How much kinetic energy do we have? I mean, I guess the one on the left is easy, right? 10 squared is 100, times 10 is 1,000, divided by 2 is 500, right? So a little bit of head math on that one, 500 joules. But somebody with a calculator, I bet you, or even you could probably do this one with head math too. How much energy do we have after? Six squared is 36 times 10, 360. 360 divided by 2 is 180. 8 squared is 64. 64 times 5 divided by 2 should be about 160. So for my money, I get 340 joules. And this is what I was saying, this is kind of a weird thing, where you can have momentum, which involves mass and velocity for these two bodies, momentum being conserved. And that's a vector conservation. But clearly energy is not conserved, right? Energy has been lost. And people say, well, where'd the energy go? Well, here, maybe we could throw this little extension in here. Oh, maybe I'll put it on the screen maybe. If I was going to extend this a little bit, where did energy go? You guys want to suggest? Where are some places that energy could have gone to? What's that?
Lost its thermal energy.
Sure, yeah. Maybe when these things bumped into each other, some heat got released. Yeah. Thermal energy loss. Where's another place it could go? Yeah.
Sound?
Yeah. The sound of the crash, right? You ever go to the train yard, you hear some crashes. Sound energy. I'm going to put out there that there could be some mechanical. You ever look at the interlocking mechanisms of trains? And if you haven't spent any time looking at trains, it's kind of cool. Like there's some really neat little gizmos to make these things latch together upon impact. But there could be some mechanical energy. I mean, we could also claim that there's mechanical energy being lost because there might have been some metallic deformation. Like I hope not. Like we didn't have like a car crash equivalent kind of thing there. But no crumple zones involved when you bang trains together. But I mean, we were kind of cruising along at 10 meters per second when we smacked into the other train. I suspect that's faster than trains want to hit each other. But anyway. All right, so we got kind of the beginnings of this idea that momentum can be conserved, but energy maybe not. And so if there's energy loss, I'm going to put out the words sort of into the ether. We're not defining them in a second, but there's this thing called an elastic collision, a perfectly elastic collision, and an inelastic collision. What do you suppose this is? Inelastic, yeah. This would be an inelastic collision. By the way, there's also something called a perfectly inelastic collision, and we'll talk about that later too. Weird that there would be something that's perfectly inelastic. That's for a later conversation.